Good afternoon, and thank you for joining me today. And my name is Yunlong. I'll be presenting my PhD thesis on learning robot control from reinforcement learning to differentiable simulation. One second. Okay, so in 2008, there was a powerful earthquake happened in China, and it located in southwest China. The earthquake was so strong that even people in Beijing and Shanghai can feel it. But due to the rough terrain, it was extremely difficult to operate the rescue, and it is impossible to send human inside into those rural areas. And the only possibility in this scenario is to fly aid to those in need. However, even today, this is an extremely challenging task due to the requirement of human pilots. And therefore, this highlights the importance of having autonomous drones for search and rescue scenarios. And this task has two important properties. The first is agility, and second is robustness. And the goal of my research is to develop autonomous control system that can enhance the agility of the robot while maintaining robustness. Okay, and this can be narrowed down to the big question, like robot control problem. And this problem has been studied extensively in optimal control. And the key idea about optimal control is basically first, derive a mathematical model for the robot and the system. And second, formulate the task as an optimization problem. And by solving the optimization problem, you can find the optimal solution for this task. It has advantages like handling constraints and also in principle optimal solution. However, it also has disadvantage like computational intensive and also require good model of the system. And on the other hand, there's entire different new discipline that studies the same problem, but with entirely different motivation. This is the reinforcement learning. And the key idea of reinforcement learning is through try and error. They solve the same problem, but they make less assumptions regarding the system and also the dynamics. Sometimes you can get some novel solutions and can adapt to changing environment. In terms of design, reinforcement learning in general is more flexible because it doesn't require, for instance, like differentiable dynamics. However, it is has high sample complexity and also has sim to real gap. So we can kind of go back in time and see what are the state of the art before I start my PhD. Okay, from the control perspective, people think optimal control is enough because we have successfully landed human on the moons using very basic control algorithm combined with common filter. And also in 2008, there's another super impressive example demonstrated by Boston Dynamics, where they show it is able to perform extremely agile maneuvers for a very complex system, use purely control method. And reinforcement learning, if you look at the same problem, they kind of live in a parallel universe. They try to solve the same problem, but reinforcement also extremely useful, and they have been used for solving many challenging problems. And one of the most notable examples is the development of AlphaGo. This is the first time that a machine learning algorithm can beat the best human in the game of Go. And they developed this algorithm using reinforcement learning. So it was kind of the beginning of the reinforcement learning revolution. And in robotics, there were also some successful stories like the quadrupedal locomotion developed by research from ETH Zurich, led by the group led by Makuta. So that kind of the big question when I start my PhD, because both optimal control and reinforcement learning have achieved impressive results. But until 2019, reinforcement mostly remain in simulation, and optimal control is good enough for most tasks. The question I discuss always with my colleague when I start my PhD is like, do we really need reinforcement learning for real world robot? If yes, how? And can reinforcement learning outperform optimal control, given that optimal control is optimal, right? To answer this question, we need a benchmark task. And in this task, good enough might not be good enough. So we need to push the controller and the robot to the limit. And this led to this application, drone racing. And by definition, in drone racing, you have to push the robot to the maximum performance in order to win. And it raises fundamental challenges for robotic research. perception, planning, control, and also learning. So the first project of my research is about autonomous drone racing. Let's first formulate the problem. So the task of autonomous drone racing is defined as flying a drone as fast as possible through a sequence of gates. And this is minimum time problem, subject to some constraints like the system dynamics, input constraints, and some physical constraints, right? And here's an animation, like the drone has to first fly through all the gates, and then you can compute the time. The one that has minimum time is the winner. This problem can be solved from the control perspective. Like you can plan a polynomial trajectory and follow with any control that you have in hand, but it's not a time optimal solution. You can also solve using optimization method, in which you first solve for the time optimum trajectory. And given this time optimal trajectory, normal controller normally doesn't work. You need a more advanced controller like multiple control. However, so this approach can provide lower bound of the lap time. However, the optimization normally takes minutes or even hours. So replanning is impossible. And the third paradigm is basically not plan a time optimum trajectory, but plan an optimum path. And instead of following the trajectory, you follow this path. But at the same time, you have to maximize the progress along this path. And it's called model predictive contouring control. And this task replanning is possible, but it is suboptimal due to the trade-off between following the path and also maximizing the progress. What I propose is using reinforcement learning. So there are two key components in reinforcement, agent and also the environment. For the drone racing task, we use simulated environment. So we develop our own simulator and we do parallelization like 100 drones in this simulator. And for the agent, we use a neural network controller, a neural network. And the observation and action, the collective thought and body rate. And also for the observation, it is basically the relative distance between the drone and the target gate and also the state of the drone. So we have all those ingredients in hand. The next we need to do is to define a reward function, because in reinforcement learning, what you define in the reward function is essentially what the policy can learn. And for this task, the high-level goal is minimizing the time, but this is very sparse signal. And instead of directly minimizing the time, we define a gate progress. And this is top-down project view of one of the segment, gate segment. And the idea is basically you maximize the gate progress with respect to the target gate. At the same time, minimizing the body rate in order to avoid oscillations. In addition, there's a binary reward, which is minus 10. If there's collision happens, then you penalize this action. And this reward is not differentiable, it's only a single value. So after we define the task, we train our policy in simulation. So we use the flight mesh simulator, parallelize 100 drones. And in total, we train for 25 million samples. And it costs roughly 10 minutes on a standard workstation. We use PPO. And this is the learning curve. As you can see in this curve, what is most interesting is that it only takes roughly 10% of the data learned to fly, and the rest of the 90% data was used to push for the maximum performance. And this highlights the difficulty of the drone racing task. And after training in simulation, we directly deploy the system in the physical world. And this shows one of the most high-speed flight we ever achieved in this lab. It achieved a maximum acceleration of about g and also maximum speed of 30 meters per second. For the sim-to-real transfer, what you need is very good system identification and also appropriate control modality, as well as a little bit domain randomization for the part that you cannot model. And we show that this neural network policy can actually push the robot to the limit, as evidenced by this plot, the throttle level. As you can see, the throttle level is mostly at 100%. It indicates that the drone is mostly flight at its maximum, as its physical limit. And on the right-hand side, you also see the battery voltage. And the battery voltage basically highlights that the policy is low pass, even though the battery we use is not exactly the same we use for the simulation. And finally, how does it compare to the optimum time? And this plot shows 5 different runs. And we show that actually the time achieved in the physical world is very close to the theoretical lower bound computed using optimization method. And in 2022, we invited 3 best humans to understand how our reinforcement learning agent compare against those human pilots. And we show that it is capable of outperforming human pilots in the competitive sport, which is the drone racing. And this video shows our drone flying during this competition day, and it flies consecutively for 3 laps, and it achieves a lap time that has much lower time than other human pilots. So we have achieved superhuman performance. We have outperformed optimal control algorithms. But what is the actually fundamental advantage of reinforcement learning over optimal control? This task of minimizing the time, whenever you have this task, you cannot mostly not solve this directly. And all these different control algorithms, doesn't matter you use MPC or reinforcement learning, tries to abstract this task into 3 different representations. As a result, we found that the main advantage of reinforcement learning over those control algorithms is because reinforcement learning can optimize a broad range of objectives, including task level objectives that gives the policy more flexibility to discover adaptive control sequences. And the optimization objective leads to better performance. And this is the main conclusion of my first work. And for the second project, I study a different problem. It's about flying through dynamic gate. But there's another motivation in which I want to start understand how can we combine the advantages of reinforcement learning and optimal control. The reason is basically reinforcement learning has its advantage of optimizing, for instance, non-differentiable reward, but it requires a lot of data for training and also cannot handle constraints. And MPC can handle constraints, but it requires all those hand tuning process. So imagine you have this task, where the task is to fly a drone through a pendulum-like gate and to reach a goal position. And this task can be solved using MPC. But how can we formulate this task? So if you want to plan a trajectory, you need to know where you should pass through the gate. You need to know basically the waypoint. But since the gate is moving, it is for sure not the current position. You need to know in advance when should you pass through the gate. But this time is also unknown. So it's like chicken and egg problem. You don't know the time, you don't know the position, you don't know the position, you don't know the time. And what we propose instead is to learn these time variables using policy search method. And the key idea is to consider MPC as a parameterized controller. And in MPC, you have a decision variable and you also have some references. And there are some unknown parameters in this example, it is the time for passing through the gate. So we don't know this and we want to learn these variables. How can we learn these variables? And we can basically formulate the search of unknown parameters as a probabilistic policy search. And this equation is very standard policy optimization objective. And you can optimize this objective using any policy gradient method. So you can basically optimize for Gaussian policy, in which you solve only for a set of fixed parameters. You can also optimize for the parameters of some function, like a linear function or a neural network function. And given those functions, you can adapt the parameters online. And in this example, we can adapt the time because it depends on the relative position, the state difference between the drone and the pendulum gate, the time variable can be different. Okay, so here is the learning curve for learning a high-level policy. So here we only learn one fixed parameters, one time variable. And the top plot shows the learning curve, and the bottom one shows how the time converges to the one that we need. At the beginning, that basically we have a Gaussian distribution, which has very large variance. And by optimizing this policy, eventually we find the time, which is roughly 1.5 seconds. And we can also learn a new network policy to adapt this time variable online. And this video shows that a new network policy is predicting this time variable online, and there's an MPC that solves the optimization for controlling the zone, at the low level. And we also deploy this system in the physical world. And this video shows how you can apply this to the physical zone. And this one is another video that captured from a different perspective. I want you to notice also the orientation of the zone. It is aligned with the orientation of the gate because we can specify this orientation reward, orientation loss in the MPC. Okay, so the third project is about differentiable simulation. We have talked about optimal control and reinforcement learning. Both have their advantage and disadvantage. And one question here is that reinforcement learning has high variance, but optimal control has low variance because it has the model to compute the gradient. But optimal control cannot leverage those neural network and large scale simulation. And reinforcement learning can leverage large scale simulation, but the policy gradient suffer from high variance. The key question is, how can we benefit from both low variance, first order gradient like in optimal control, and also large scale simulation data? And the answer is to use differentiable simulation, or that's one way of doing this. So we have this general problem formulation where you have a cost function to minimize. Normally, the decision variable is just the control command. And here we assume that the control command is derived from some function like a neural network. And we want to find the gradient with respect of the loss function with respect to the parameters of the loss of the network. And basically, you can expand this function and get the analytic gradient for updating updating the policy parameters. And this equation contains two important components. One is multiplication, which indicates you have to do back propagation through time. And there's also this partial derivatives. And this is basically the derivatives of the robot dynamics, meaning the model has to be differentiable. And in the context of quadruped robot, normally it is not differentiable, or there's due to the contact, or there's a discontinuity in quadruped robot. But we can also simplify the robot model using single rigid body dynamics. And this is the equation. And this function basically takes the ground reaction force from the leg that has contact with the ground and taking this as the control input. And you can do the integration, forward integration, and get the corresponding position, orientation, velocity, and angular velocity of the body pose. So the big question is, how can we compute the gradient? And the answer is use automatic differentiation. And this is an example. Imagine you have a function z equal to log x times y. You can build a computational graph. And then for forward propagation, you forward propagate through this graph and to get the output. And for backward propagation, you can compute the gradient. And this is the same concept for differential simulation. Basically, you build a computation graph, roll out the trajectory. In the end, you get a kind of huge computation graph, but you can compute the gradient and backpropagate through this entire graph directly. And we show by doing this, there's a huge advantage for learning locomotion policies. And this plot, sorry, I forgot to put the index. And the blue line indicates the differential simulation, and the green one indicates the differentiable simulation. So basically, we see that when you have the analytic gradient, you can optimize the policy much more efficiently. We also show that you can directly deploy this policy to the real world. And this is an example of using neural network controller for controlling the mini cheetah robot. And this control policy has some robustness, like it can handle those soft terrain and can work forward, backward, and also can have different control, like the pattern. I want to mention this is one of the first demonstration of using differentiable simulation for controlling the quadrupedal robots. Before that, most of the research was done in simulation. Okay, so let's go back to this big picture and see what we have done so far. So after I started my PhD, I think the demonstration of using reinforcement learning for pushing a super agile robot to its physical limit and also achieving superhuman performance is a milestone in learning for robotics. We show that it is possible to outperform open control in such difficult tasks. And the second contribution is more on a control perspective. We demonstrate that you can use NPC for traversing through dynamic environments. This is quite agile maneuvers. And we can also look at this contribution from a unified perspective. Basically, we provide insights from different angles to look at the control problem. We look at reinforcement learning and optimal control. We look at how can we use reinforcement learning for optimal control. And finally, we can even consider reinforcement learning as optimal control, in which you can use the model. So, but this research also has limitations. So we have an agent, we have an environment. For the example that I gave at the beginning, sending a drone for search and rescue environment, can we do it? We can still not do it. The main limitation is due to the lack of using observations from the drone directly. So we still rely on VICAN, motion capturing system for state estimation. And one of the most promising future direction, I think, is representation learning. How can you abstract the state and the features from purely observation? And this observation can be multimodality, including IMU, images, LiDAR, or whatever sensor you have. So yeah, and also 3D representation learning. We are living in a 3D world, and we need to understand the 3D environment. And second one is the objective formulation. All those examples you see has a reward function or loss function that is designed by me and takes a lot of time. It's not general. When you have a new task, you need to define a new objective function. So how can we formulate the objective in a more general way? And finally, is the environment. All the models we use are based on first principle model. It is not accurate. It is also sometimes can be off. So can we do better? For example, can we learn directly from real world? And this can go to the direction of model-based reinforcement learning, where you first learn a word model and then use this word model to do, for instance, like backward propagation. Okay, one more thing. I think I still have time. So this research is based on two important software that we developed in our group. One is Flightmare Simulator, and second one is Agilicious Control Stack. And I want to highlight it is very important to open source framework for robotics research, because building those tools takes a lot of time. And also, when you share the software, you can achieve much more than just doing this alone. And this simulator and also Agilicious are now standard tools in our lab. And even going beyond research, I have seen many master students from different countries using the tools we developed for the master thesis. And also next semester, there will be new course on vision-based flights organized by my colleague Leonard and also Uncle. And we are using those tools we developed for education, the next generation robotics. Okay, with that, I want to thank you for your attention. Yeah.
Thank you for your presentation. Now we can start with the questions. As I said before, we start with the furthest geographically. So I guess this is